In today's talk, we will discuss radioactivity, the radioactive decay, the decay laws, and energetics. Then we will discuss properties of radioactive materials, then artificial radioactivity and its comparison with natural radioactivity. Then we will go through the conservation laws and modes, and then we'll start discussion on alpha decay. And in this regard, Geiger-Nuttall rule for alpha decay will be discussed. It started with uranium. The radioactivity of uranium was discovered by Henry Becquerel. He was born and educated in Paris. His grandfather, father were also physicists, and all of them turned into professors at Paris Museum of Natural History. His grandfather and father had specialized in fluorescence and phosphorescence. In 1885, Henry Becquerel placed a fluorescent uranium salt on a photographic plate and covered it with the black paper. He exposed it to sun and found that plate fogged. When he developed it, it was fogged. Becquerel repeated the experiment, but the clouds obscured the sun for several days. And when he developed the plates anyway, to his surprise, he found they were as fogged as before. So he identified eventually the source of penetrating radiations as uranium in the fluorescent salt, and the radiations were coming out of the uranium, and these were capable of ionizing the gas and consisted of fast charged particles. He received Nobel Prize in Physics in 1903 for his discovery of radioactivity. If we look at the name of radioactivity, it was given by Marie Curie. She described it as a mysterious effect of uranium operated through invisible rays. Radium proved invaluable material in further studies of radioactivity and atomic structures. Marie Curie was a student at the time of Becquerel's discovery. Curie decided to study uranium. She realized that radioactivity was a property of uranium. She also discovered that and separated that the radium and polonium, and then eventually plutonium, all emitted radiations. She was pioneered in the discovery of medical use of X-rays, and then, as we know very well, that she is a lady who was awarded 2 Nobel Prizes, one in physics and other in chemistry. Radioactive decay and its energetics we need to study, and decay can be described through quantum mechanics. It is a pure random process, and it has a constant probability of decay for a single nucleus to decay into a daughter element. So if we consider n number of nuclei that belong to a parent element, and each one has a decay constant or a decay rate, the decay is per second of the parent nucleus, then we can write this differential equation in which the changing number of parent atoms, dn, is actually proportional to the original number of atoms, the parent atoms, and the delta t time for which we study the decay. and the proportionality constant is lambda. And since the number keeps on decreasing, therefore the minus sign. If we integrate this equation for from time t is equal to 0 to certain time t, and at time t is equal to 0, if the number of atoms are n naught, then we have the resulting equation as n of t equal to n naught multiplied by e to the power minus lambda times t. Here e is the exponent, the log's base, and its value is 2.7. From the same equation, we can find out the average life of the decaying element equal to 1 over lambda, and we call this capital lambda. The half-life is the life or the time taken by the parent elements to decay into the half of the original. The time for which they become half is the half-life, and it is given by natural log of 2 divided by the lambda, or natural log of 2 multiplied by the life. Remember that lambda has the units of decays per second. That is, units are number divided by second, or second inverse. So when we see this equation, e to the power minus lambda times t, the lambda multiplied by t is a dimensionless quantity, and e to the power some number. And minus sign stands for this fact that this is going to decrease. So e to the power minus lambda t is actually a decreasing function of time. Let's go through a few properties of radioactive decay. For radioactivity, the properties are following. Radioactive decay will change one nucleus into another. If the product nucleus has a greater nuclear binding energy than the initial nuclear decay, this will happen, because greater binding energy is a guarantee that it will become more stable. The difference in binding energy determines what kind of decay will occur, which decay are energetically possible and which are not. Nuclear phenomena is really a random process, and radioactivity is a nuclear phenomena, and it is due to instability of the nucleus. Nucleus has two types of forces, primarily the strong nuclear force and the Coulomb repulsive force, and the number of protons and the number of neutrons dictate these the instabilities. This radioactivity is a spontaneous process, and it cannot be reversed. Spontaneity stands for the fact that it happens on its own, and no other affecting force will trigger it. Further properties: it is independent of the external factors such as pressure, temperature, state of the substance, electric field applied, magnetic field applied, or the types of the crystals. Radioactive elements can emit alpha particles, they can emit beta particles, they can emit gamma rays. These are three important radiations that can be emitted. They are probable in nature, and a radioactive element does not depend on the age of the nucleus or how it was created or the age of the material. A radioactive element does not emit alpha particle and beta particle together. Simultaneously, both of them cannot happen. One after the other can happen. Physical and chemical properties of the daughter element, the byproduct, are different from that of the parent. And this is really the signature of a radioactivity, that it is a nuclear property. Let's briefly discuss artificial radioactivity and compare it with the natural radioactivity. Radioactivity is basically due to the instability of the nucleus, and the decaying of the nucleus will take place in nature, as we know, if the number of protons and the number of neutrons have a strong imbalance, and the force of attraction and the force of repulsion has imbalance. However, there are elements beyond uranium that have shown the artificial effects. And when we create these artificial, they are the transuranic elements. They can be made to disintegrate into the other elements by colliding with the slow-moving neutrons, or with the protons, or with the photons. And the process is called artificial radioactivity, or production of artificial radioactivity. We can make a stable element into an artificial radioactive element by injecting neutrons or protons or photons. If we compare the natural radioactivity with the artificial radioactivity, we see that in natural radioactivity, it will take place on its own in nature. However, artificial radioactivity can be induced by man in a laboratory. Natural radioactivity will occur in elements with the atomic number greater than 82. Artificial radioactivity can be induced in elements with the low atomic numbers as well. Natural radioactivity has usually long half-life. Half-life means the life or the time period after which the parent elements reduce to half of its original size. Usually, in artificial radioactivity, the elements are short-lived and their half-life is short. Decaying particles in natural radioactivity are alpha particles, beta particles, and gamma particles. In the decay of artificial radioactive material, alpha particles, beta particles, the beta minus and the beta plus can be emitted, and gamma. Let's briefly talk about the governing conservation laws in radioactive decay. Conservation of energy is the first, that is, in the process, the energy is conserved. Suppose a nucleus decays into Y with the emission of X. Here we show this reaction. X is going to Y with X, small x, and the Q value of the reaction takes place, that is, the energy is emitted. Now we convert this into the mass balance and then energy balance. The initial mass of the X multiplied by C square gives us the energy, and then the mass of Y, C square, is the energy for the daughter element, and X is the emitted particle, its mass multiplied by C square, and the Q value. So the Q value is basically the mass of the original parent element minus the mass of the daughter element minus the mass of the emitted particle, whole multiplied by C square. And this energy will appear as the kinetic energy of both the capital Y material, that is the daughter element, and X, the emitted particle. If the emitted particle is very small, it will carry most of the energy. It will carry more energy of chunk of this Q. The conservation of linear momentum is the next important And in this, and suppose initially decaying nucleus is at rest, then the total momentum of the decaying product must be zero. So they will be emitted in the directions opposite to each other to conserve the momentum and make the vector equal to zero. The conservation of the angular momentum stands for the fact that the angular momentum before the reaction and the after reaction must remain constant, and the total spin angular momentum before decay and the total spin angular momentum after the decay must remain the constant. And for example, this is a neutron decaying into a proton, an electron, and an antineutrino, and then the spin, the angular momentum is originally half. The spin of the proton is half, the spin of the electron is half, and the antineutrino spin is minus half, and therefore we get the balance. We have the conservation of the total electric charge before the reaction and the after reaction, and we have also the conservation of the mass number before the reaction and the after reaction. The total nucleons remain same. Very interesting is the case that when radioactive decay occurs, it is a process which involves unstable nucleus, the parent nucleus, and it transforms into a stable daughter nucleus, and it emits particles or photons like X. And then we call this X as emitted radiation, and then it has some energy of the reaction, and the energy of reaction is distributed between X and Y. Since radioactivity is a spontaneous process, the radioactive tracers behave same in chemical and physiological processes as their stable counterparts, but they are radioactive, and that's the only difference. Let's see few important decay processes that are there. For example, decay by beta emission, and I mean to say the beta, we will discuss more in detail the beta particles and the beta decay. There are two different types of beta decays, the beta plus decay and beta minus decay. And the decay by the beta and the gamma, it is a beta which is connected or associated with a gamma. There is a beta decay, and then there is a gamma decay or a cascade gamma decays. Such elements do exist in which first beta decay happens, and then the daughter element gets further converted into a stable daughter element by emitting gamma rays. The isomeric transitions are also of interest. We will discuss more about this in coming lectures. Internal conversion of the nucleus takes place, and we will talk more about this. Electron capture is also a very important phenomena, and it is part of the radioactive decay. The electron conversion and then translation of the nucleus by emitting a gamma is also there, and we will talk about the beta plus emission and the electron conversion. Decay by the alpha emission is the today's talk also, and then fission and fusion processes that are also really in the category of the decay, but they are originated by the instability created in the nucleus. Let's see the properties or the characteristics of alpha decay. Alpha particles are basically helium nuclei. Helium nuclei, because alpha rays are consisting of positively charged particles that are carrying +2 unit charge, and the mass is almost 4 atomic mass unit, and therefore it resembles with the helium nucleus. They affect the photographic plate. The alpha particles do affect the photographic plate. They are deflected only slightly towards the negative plate in electric field. They also get deflected in magnetic field. So they are charged, and hence the Lorentz force is in action for these alpha particles. Alpha particles can ionize gas. Alpha particles have maximum ionizing power. These particles will interact with the medium as they are charged, and they will create electrons and ion pairs as they move through the medium. And they can be very easily stopped by a piece of paper, so they can be shielded through a piece of paper or by aluminum foils. The very small thickness of material will stop. They have velocities of the order of 1 into 10 to the power 7 meters per second, and they have very little penetration. The mass is culprit because they are the helium nuclei. They are heavy, so they cannot travel far. The alpha decay is basically constrained to conform the same conservation laws and the other processes, that is the mass energy conservation, charge conservation, linear and angular momentum conservation, the number of nucleon conservation, the number of lepton conservation, that is the charge conservation. So for radioactive substance that is found in nature, half-life is not shorter. They have the larger half-lives. And we have seen that the radioactive substances are continuously being produced in nuclear reactions and in the nuclear transformations. Now the question is that to be a radioactive material, nuclear mass must be greater than the mass of the decaying product or not. Many heavy nuclei are unstable, and since the Coulomb barrier is basically there, which inhibits the decay of the nucleus, so this means that alpha particles must tunnel out through this positive Coulomb barrier. If you recall this energy, this diagram, you can see that the potential energy originally for the nuclear potential is a potential well type, and it is an attractive potential which keeps the nucleons inside, and for certain distance r naught, it starts becoming positive, and then it starts decreasing as the Coulomb potential decreases with the distance as 1 over r behavior. Now this is the case when if the alpha particle energy is this much. It is not here within the potential well. It has energy higher and positive value of energy, some larger value of energy. Still, it is inside this well. It is not over this barrier. Then this type of alpha particle can penetrate through this and come out. So this positive barrier can be penetrated through. And we now know that this is possible after learning the quantum mechanics. So there is a relationship between the half-life or the decay constant and the decaying energy, and it exists. And for a Coulomb barrier penetration, alpha decay is really very, very popular. We know very well now that the electrons in the Coulomb barrier of atom can also penetrate through and tunnel through. And these tunneling electrons are very useful, and they can be very helpful in telling the story of the structures of the atoms. As we move further, the alpha decay or the penetration of the alpha particles through the positive Coulomb barrier has enabled us to look into the nature such happening for other types of processes. For example, the electron in multi-electron structure, where there is a positive repulsive positive barrier and the electron do penetrate out. Similarly, the tunneling of the mass confined to a black hole, where the mass can tunnel through the barrier penetration as a leakage of mass through the black hole. And that's how the black hole can evaporate. We will very briefly introduce the Geiger-Nuttall relationship. In 1911, the Geiger-Nuttall made a plot or a graph for the decaying constant lambda versus the kinetic energy of the alpha particles. They had the source that was made available through Curie's, and from that Curie's source, they had the alpha particles, and the different energies of the alpha particles were used, and the graph of the decay constant and the energy was made, and it behaved like a straight line with on a logarithmic scale. If there is a log-log scale on x-axis log and y-axis log, then this is a kind of a straight line where a and b are constants, and they can be determined through experiments. The Geiger-Nuttall law also relates the decay constant of the radioactive isotopes with the energy of alpha particles, and the rule is that the short-lived nuclei emit more energy. Here, lambda, if you look at the lambda and recall the average life or the half-life, it is in inverse proportional. So I can replace this lambda by 1 over half-life. So if I increase the energy of the alpha particle somehow, then I find that for those having more energy, the half-life is going to decrease. So if the value of the half-life is small, 1 over half-life will be large, so the energy will be. So rule is that the short-lived nuclei emit more energy than the long-lived ones. The long-lived ones are not emitting that much energy. So probability that an alpha will penetrate the barrier or any one will approach will depend on the transmission coefficient. And we will talk about the transmission coefficient further in coming lecture. The frequency or the probability of this decay will depend on the transmission coefficient multiplied by the frequency at which you approach the barrier or the alpha particles hit the barrier. So this frequency is given by the velocity divided by 2r. 2r is the diameter of the nucleus, the potential well, width of the potential well, and that's how we find out the frequency. So to sum up this whole discussion, I can safely say that this leads us to the half-life or the decay constant related to the transmission probability, this t, and the radius. If the radius is small, we know the radius of the nucleus depends on A, capital A. Large nucleus will have a large radius. Large radius means the small value of lambda. Small value of lambda means the large value of half-life. So large radius, large half-life, small probability of decay. So the half-life is given by this relationship, in which if you substitute the energy, you get this balance, that the alpha particle energy and the half-life are inversely related through this power relationship, e to the power minus half, and E alpha is in million electron volts. So if you substitute 2 million, you substitute here 2, and you find that the log of the T, and you can find out the half-life, and the half-life will be, for larger value of the energy, the half-life will be short. And for the large value of half-life, the energy will be small. So we stop here today's talk, and we will continue our next discussion on the alpha decay from here onward. It needs further clarification and a little bit use of quantum mechanics. I will not go into the derivations, but I will simply elaborate how fancy and how beautiful the results come with the help of Schrödinger wave equation. If we subject that equation to such a nuclear potential, tunnel-like potential, and a Coulomb barrier. Let's stop.